Hello, dear students. Good evening. So, in the previous class, we have completed the chemical properties of haloalkanes and haloarenes, nucleophilic substitution reactions of haloalkanes, SN1 mechanism as well as SN2 mechanisms we have completed in the previous classes. So, in today's session, we'll discuss about a simple concept that is about the stereochemical aspects of haloalkanes and haloarenes. That is chemical reactivity. Stereochemical aspects, some basic principles, some terms involved in optical isomerism and optical activity. So, what is the product, the geometry of product obtained during the reactions of haloalkanes and haloarenes? Stereochemical aspects of SN1 and SN2 mechanisms. So, in that, so first let's basic point optical activity and optical isomerism. Let's start some basic points. So, now in this topic, let us discuss some basic terms which is involved in optical isomerism. Dear students, as we have already studied in class 11th, the concepts of isomerism. Can you define what is meant by isomerism? As you know that two or more compounds which having the same molecular formula but differ in the structural formula are called as a structural isomers. Similarly, if they having same molecular formula as well as the same structural formula, but they are differ in spatial arrangement of atoms or group of atoms around the central metal atom, are called as stereoisomers, and the phenomenon is said to be stereoisomerism, right? So two or more compounds having the same molecular formula, same structural formula, but different in spatial arrangement of the constituent atoms or group of atoms. So here, so to understand this concept, optical activity and optical isomerism with the stereochemical aspects of the reactions, let us discuss some of the basic terms involved in this. So the first one is the plane polarized light. So in this, the first basic terms involved, that is plane polarized light. So take the heading. What is the definition of this term? Plane polarized light. Plane polarized light. What is meant by this plane polarized light? PPL, plane polarized light. So here, as we know that ordinary light consists of electromagnetic radiations and which are vibrating in all the directions. So let us consider an ordinary light. So this is an ordinary light which vibrate in all the possible directions. The ordinary light which consists of electromagnetic radiations which vibrate in all the directions. Ordinary light, when this ordinary light, when it is passed through a nickel prism, when it is passed through a nickel prism, this is a special type of prism, nickel prism. It is made up of crystalline, it is a special type of prism made up of crystalline calcium carbonate, made up of crystalline calcium carbonate. Calcium carbonate preferably it is exists in amorphous form, but in crystalline calcium carbonate it is made up of crystalline calcium carbonate. When the ordinary light is passed through the nickel prism, so it becomes a plane polarized light. It becomes a plane polarized light. That means it consists of the electromagnetic radiations which vibrate only in one direction and the remaining are cut off. So this is said to be a plane polarized light, PPL, plane polarized light. That means which consists of electromagnetic radiation which vibrate only in one direction, that is said to be a plane polarized light. and this is ordinary light, which consists of electromagnetic radiation and which vibrate in all the possible directions. So this is PPL, plane polarized light. Now, optical activity, an optically active compound, if you want to say, optically active compound, that means a particular compound we are selecting. We want to know that whether the compound is optically active or optically inactive. So that can be decided based upon, or by using this plane polarized light, we can find out whether the compound is optically active or inactive. So how we can determine? So look at this. If uh, an organic compound, its solution is taken in a test tube or any other tube, and through this, if the plane polarized light is passed through this solution, then we can observe three possibilities. Number one, this plane polarized light, it may remains as it is, it may remains as it is, or it may. So look at this first one. The plane polarized light initially vibrated in one direction, and this light, it may rotate it towards right side, it may rotated towards right side, or it may rotated towards left side. The plane polarized light, it may vibrate, or it is rotated towards right direction or left direction, or it may remains as it is. It do not rotate the plane polarized light. So this is depends upon the nature of compound that we have used in this tube. So here I have taken the organic compound, solution of organic compound. Now, if this compound is said to be optically active or inactive, that depends upon the rotation of this plane polarized light. See, if the organic compound which rotates the plane polarized light either towards the right direction or towards left direction, I'm not saying in particular one direction, either towards right or towards left, then the compound is said to be optically active. It is active, optically active compound. Is it clear? The compound which rotates the plane polarized light towards either towards the right direction or towards left direction, then it is called as optically active compound. If the compound, if the organic compound which do not rotate the plane polarized light, then it is said to be optically inactive substance. So here in this case, the light is not rotated towards any direction, therefore we can say that this in this case, this is optically inactive. This is optically inactive. It is optically inactive. Whereas in these two cases, we can say that these are optically active. This is optically active compound. And in this, the light, if it is rotated towards the right direction, it is rotated towards the right direction, towards the right, then it is said to be dextrorotatory. It is said to be dextrorotatory. If the light is rotated towards left side, then it is said to be levorotatory. Levorotatory. This is said to be L form, L compound, or this can be represented by D, or it can be represented by the symbol plus, and this can be represented by the symbol minus. Either you can write plus or you can write minus. So that is, the compound is said to be, for example, if an organic compound we have taken is lactic acid. Lactic acid. Suppose if it is lactic acid, or any compound you can take, any organic compound. So this can be represented by using the term D or L, or we can represent the sign plus instead of D, we can represent by using plus, R we can represent by using minus. D lactic acid, L lactic acid, or plus lactic acid, minus lactic acid. So this represents, this term D represents that, D represents that dextrorotatory. D, it represents dextro. That means this compound which rotate the plane polarized light towards the right direction, whereas this L stands for, it is levorotatory, levorotatory compound. That means the light is rotated towards the left direction. Is it clear? Yes, the first point is plane polarized light, plane polarized light. And the second concept is whether the organic compound is optically active or optically inactive. So, very simple concept. If the organic compound, the solution of the organic compound, which rotate the plane polarized light towards either towards right or towards left, then it is said to be an optically active compound, or else it is optically inactive. Is it clear? Now, the one more specific terms we are using here, that is specific rotation. Specific rotation. So, what is meant by the term specific rotation? No, specific rotation. Specific rotation. Specific rotation of specific rotation. This specific rotation is nothing but, so this is the plane polarized light. That means let us consider only one direction. Now, this plane polarized light, when it is passed through an organic compound, it either rotating to, this is an organic compound, when it is passed through this, now this compound, it is either rotated towards the right direction or towards left direction. Any one you can consider. Now, the degree of rotation, how much degree, the number of degree of rotation caused by this substance is said to be specific rotation. Now we can define specific is nothing but, so here this specific rotation can be defined as, or it is represented by alpha, that is specific rotation, with the symbol D. It stands for the wavelength of light used at a specific temperature T, that gives us to some values, and in bracket we can represent concentration, comma, its value, some x concentration. C represents concentration, and after this you can write some value, some values x. So this is the representation of specific rotation. So this is specific rotation can be defined as, how we can define this specific rotation? Look at this, very simple definition. So here this plane polarized light is rotating towards right or towards left. The number of degree of rotation observed by 1 gram of substance in 1 ml of solution taken in a tube of path length 1 decimeter. The specific rotation is nothing but the number of degree of rotation observed by 1 gram of a chemical substance, 1 gram of chemical substance taken in 1 ml of solution, 1 gram of substance in 1 ml of solution, and this is taken in a tube, this is taken in a tube of having the path length 1 decimeter, 1 decimeter. The path length is 1 decimeter, 1 centimeter cube or decimeter cube, dm cube, 1 dm cube, decimeter, sorry, dm cube, not 1 decimeter, just 1 decimeter. So that means 1 gram of the organic compound is dissolved in 1 ml of solution, and that is taken in a tube having a path length 1 decimeter. So its concentration is expressed in terms of what? So its concentration is expressed in terms of grams per ml, grams per ml. The unit of concentration is grams per ml, because specifically 1 gram of substance is dissolved in 1 ml and it is taken in a tube having a path length 1 decimeter, then 1 decimeter, and with a wavelength of d light. Particularly sodium light is used to 586 or 589, in between that range, 586 to 589 nanometer of wavelength light is used preferably. So this is the plain polarized light. I am saying this is plain polarized light, and this comes from an ordinary light. So this ordinary light, its wavelength is approximately, wavelength is 586 to 589 nanometer we can use. That is a sodium lamp. Sodium lamp, it is a characteristics of sodium metal, right? Okay, so with d, it stands for the wavelength of light used at a specified temperature T. Temperature must be specified at constant temperature. So this is said to be an specific rotation. Is it clear definition? You can note one more time. We can repeat. Specific rotation is nothing but the number of degree of rotation observed by 1 gram of substance in 1 ml of a solution taken in a tube of path length 1 decimeter by using a D light at specified temperature T. This is called specific rotation. Specific rotation. So an optically active compound is nothing but which rotating the plane polarized light either towards right direction or towards left direction. And the extent of rotation that depends upon its concentration, temperature, and the wavelength of light used in this case. Okay, this is about the specific rotation. Now we have discussed about the simple concept, that is plane polarized light, optically active substances, and specific rotation. Specific rotation. Now let us study about the molecular symmetry or asymmetric carbon atom. What is meant by asymmetric? Chiral carbon atom. Symmetry or chirality of an object or molecule. Molecular asymmetry and chirality. So the next heading, molecular asymmetry. Molecular asymmetry and chirality. Chirality of an object, or you can say of a molecule. Chirality of an object or chirality of an molecule. What is meant by this chirality? And already we know that optically active compound. That means if an organic compound in which look at this. So preferably methane, ethane, propane, butane, butanol, chlorobutane, etc. different organic compounds. You know the example. In such any one organic compound, if it contains a carbon atom, the carbon atom to which, if the carbon atom is attached by 4 different groups, completely different groups, let us call this as group A, B, C and D. The carbon which containing 4 different group is said to be an asymmetric carbon, which is represented by the star mark, and this carbon is said to be asymmetric. This carbon is said to be asymmetric carbon. Asymmetric carbon, or it is also called as, simply it is also called as, it is chiral carbon atom. Chiral carbon atom, or it is also called as stereocenter. Stereospecific center or stereocenter. Stereogenic center or stereocenter we can call. Asymmetric carbon atom, the carbon to which 4 different groups are attached is said to be an asymmetric carbon atom. For example, you can take example. So methane, CH3 methyl group, a carbon to which one hydrogen, and this side one chlorine group, and here CH2 CH3, CH2 CH3. So to this carbon, the carbon on which I have written the star mark. So to this carbon atom, one group is methyl group is attached, one group is chloride ion, one group is hydrogen, and the other group is ethyl group. So therefore, here to this carbon atom, four different groups are attached. Therefore, we can say that this is an asymmetric carbon atom, asymmetric, or we can call chiral carbon atom, chiral carbon atom. So if the compound which containing an asymmetric carbon atom, chiral carbon atom, or a stereo center, so this is called stereogenic center or asymmetric chiral carbon atom. If the compound containing asymmetric carbon, then this has a tendency to rotate the plane polarized light either towards right direction or towards left direction, then only we can say that it is an optically active compound. If it do not containing the chiral carbon atom, then it is an optically inactive. If the compound which containing an asymmetric carbon, then only it rotate the PPL, plane polarized light towards right or left. Then that is said to be optically active compound, or else it is optically inactive. Make clear that. So number one, for optical activity, the compound must and should containing an asymmetric carbon, that is chiral carbon atom. The second point, it must and should rotate the plane polarized light either towards right or towards left. Is it clear? So here, if this compound is used, so it gives, so as we know that carbon is tetrahedral in its geometry, structure of organic molecule, if we return, then it is said to be tetrahedral structure. Carbon, carbon, one tetrahedral structure. So this is the tetrahedral structure, and in this tetrahedral structure we can write that one of the bond is behind the plane, so that is represented by solid wedge behind the plane, one is above the plane, one is above the plane, so this is above the plane dash solid, solid wedge dash wedge behind the plane, above the plane, and these two are on the plane. So let us call this as A, B, C, D. A, B, C, D. Or you can write little cross. A, B, C, D. Molecule A, B, C, D. That is, this carbon atom is an chiral carbon atom. Chiral carbon atom. Now, if we consider its mirror image, mirror. So in front of mirror, it looks like as this is the carbon, carbon, and preferably the B, C, and this will be A, this is A, and one more term, this is P. This is the solid wedge, solid wedge, right? Huh. Okay. So if these two are mirror images of each other, A, this is B, C, and D, and this is the chiral center. Look at the structure A and B, structure number 1 and 2, structure 1 and structure 2. These two structures are mirror images of each other. Yes or no? So these two structures are mirror images of each other. So if we draw uh, our hand, this is one hand, This will be the mirror images of, exactly, this will be the mirror image of the other one. Other one I am writing here. Exactly, it is opposite. The right hand side and left hand side are the mirror images of each other, but these two are non superimposable on its mirror images. You can see here. So our left hand side, when you look at in the mirror, it looks like, and it is a right hand. So these two are the mirror images of each other. So these two are mirror images of each other, but these two images are not superimposable on each other. So it is completely different. So the an object which have mirror images and which are non superimposable mirror images, the object which having non superimposable mirror images are said to be chiral object or chiral molecule. The molecule the molecule which contains the molecule which contains so this is one structure, or simply we can take an image a. This is a mirror images, its mirror image like exactly same, and these two are exactly superimposable on each other, right? So these two are the mirror images and it can superimpose on its images. If I am considering the letter B, then its mirror image is, it is, this is the mirror image of B, and these two are non superimposable. So superimposable mirror images, non superimposable mirror images. So in this case, if an object or molecules which gives non superimposable mirror images, then the molecule or object is said to be optically active, and this is possible only in case of the compound which do not containing any symmetry, or we can say which containing an asymmetric carbon atom. If the compound containing asymmetric carbon atom, then asymmetric carbon atom means it do not containing any symmetry. So therefore it can rotate the plane polarized light towards left or towards right. Therefore it gives the mirror images and which are non superimposable on each other. So therefore this object or this molecule is said to be chiral molecule, chiral molecule or asymmetric molecule. Chiral molecules are asymmetric molecule. So here these images are called images are also we can known by the term enantiomers. These terms are said to be enantiomers. Enantiomers. Enantiomers is, it can be defined as the optically active compounds which having non superimposable mirror images are called as enantiomers. The non superimposable mirror images are called as enantiomers. So these two images are said to be enantiomers, whereas these are not. These are not enantiomers, but these two are enantiomers. Reason? Because these two are mirror images, these two are A and A, these are mirror images, but it is superimposable and B is non superimposable. So these non superimposable mirror images are called as enantiomers. Non superimposable mirror images are called as enantiomers. Is it clear? Yes. So up to this we have completed the molecular symmetry and chirality of the object. Molecular symmetry and chirality of the object. So here the one more terms we can represent, the molecular dissymmetry, dissymmetry and the molecular dissymmetry and chirality if you want to consider. So molecular symmetry, symmetric and asymmetric. The asymmetric we are saying that it is a dissymmetry. If a molecule which having any one kind of symmetry, it may be a plane of symmetry, a center of symmetry, an axis of symmetry, etc. If a symmetry or a plane or an axis, when it divides the two molecules into two equal halves, then if it produces a mirror images of each other, then the compound is said to be optically inactive because it containing a symmetry. So that means a plane of symmetry, for example, if we are considering a box. So if this object, when it is divided into two halves, so this is a plane which dividing an object into two equal halves, and these two halves are mirror images of each other. In that case, if it is a mirror images of each other, then these two are said to be, if it is a mirror images, then it is said to be it containing a plane of symmetry. If it having a plane of symmetry, then it is not an optically active compound. So for optical activity, it must and should containing asymmetric center carbon atom, asymmetry. But here it is, and symmetry is present in this molecule. Therefore, we cannot say that this is an optically active compound. We cannot say that. So it is an optically inactive molecule. Let us consider a few example. CH3 carbon, C, CH3, 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 H and OH. That is 2 propanol, 2 propanol. So 1, 2, 3 propane, 2 all, 2 propanol. If we are considering the mirror images of this, when it is considered its mirror images, it gives H O, HO, one carbon and another hydrogen, CH3, and this is an another CH3 molecule. Whether this is an optically active compound or optically inactive compound, can you predict? These two structure I have written here, the mirror images of 2 propanol, 2 propanol, 2 propanol. Whether it is an optically, 2 propanol is an optically active compound or not. So directly you can say whether it is optically active compounds or not just by looking at the structure. So because this carbon atom, first I have written the structure, and check the any carbon atoms, you can check any carbon atom. So if it contains, if it contains CH3, CH3, CH3 propane, 2 propanol. So this is the complete structure I have written. So you can check any carbon atom whether it is symmetric or asymmetric center. First, this carbon atom. So this carbon atom is attached with 3 hydrogen. These are the same group, therefore it is not an asymmetric carbon. But this carbon is an stereo center because this carbon containing one CH3 group, this is an another CH3 group, same groups are there, we cannot say it is stereo center because two groups are same. The carbon is said to be chiral carbon atom only if it containing 4 different groups. So here two groups are same, CH3, CH3, same groups are there, and this is hydrogen OH, it is different, but two groups are same. All the 4 groups are not different, therefore this carbon do not containing an asymmetric carbon atom, therefore it is not an optically active compound, not an optically active compound. By looking at this structure, optically active compound means it must and should have non-superimposable mirror images. But these two are non-superimposable mirror images because, okay, mirror images are there when you place one on other, these are non-superimposable. But when you rotate this one of the mirror image by 180 degree, when you are rotating this by 180 degree, then it gives exactly same structure, it gives exactly same structure. So this, when it is rotated by 180 degree, when it is rotated by 180 degree, then it gives a structure which is exactly similar to the first compound, similar to the first compound, OH, H, CH3, CH3. Now you can check the structure number 1, structure number 3. It is second one and this is third one. Structure 1 and 3 are mirror images are there, but they are superimposable on its mirror images. So this is the mirror image of 1, but when it is rotated through 180 degree, now these two 1 and 3 structure are exactly superimposable on it. So therefore it is an not optically inactive compound. So instead of this example, if we are considering 2-butanol, let us take another example. 2-butanol. It is 2-propanol I have considered. Now let us consider 2-butanol. But, ane, 2, all. 2-butanol. So let us write the first structure. CH3, CH2, CH2. It is butane. Second position, one OH group. Second position, one OH group. Remaining all are hydrogen. Now you can check how many chiral carbon atoms are present in this. How many chiral carbon? This carbon is chiral or not? No, it is not a chiral carbon because it containing 3 hydrogen. This carbon, yes, it is, of course, it is a chiral carbon atom because on this carbon atom, one group is OH, second group is hydrogen, H and OH, different groups. Third one is methyl group, it is third, it is again it is different, and the fourth one is ethyl group is attached. Yes, so it containing one chiral carbon atom. Now you can check this one. So this carbon containing 2 hydrogen same group and the last one containing 3 same groups. So therefore 2-butanol it containing one chiral carbon atom. Over. If one chiral carbon atom is present, it is understood that yes, it is optically active compound, because the compound which containing the chiral carbon atom which rotate the plane polarized light either towards right or towards left. Therefore it is said to be an optically active compound. Or you can consider its images. So this object or this molecules which do not give superimposable images. So these mirror images are always non-superimposable. You can check the structure. So first carbon 1, 2, 3, 4. Mirror images 1, 2, 3, 4. 1, 2, 3, 4. So one positions will be fixed. So let us take this is a consider this is a mirror images of each other. Mirror images. Now in this case, let us put a number. Fix one group. This is the hydrogen. 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 Next group is CH3. CH3. C2H5OH. When it check the mirror images, this will be the CH3 group and this is C2H5 and this will be the OH group. OH group. When it is rotated through 180 degree, so what happens when it is rotated through 180 degree? So this gives an structure. So see, so from this to this I have rotated through 180 degree. I have rotated, so this about this axis. So this is the hydrogen I have placed fixed position and I have rotated this by 180 degree. So when this is rotated by 180 degree, the OH will be on this side. Okay, this is the OH group when it is rotated, OH group. But CH3 and C2H5 groups are interchanged here, CH3 group, because when OH comes here, so the last group CH3 will be in the OH position. So this group will be changed. So therefore, so this gives C2H5 and this is CH3. Now you can check these two structure. H superimposable, okay. OH superimposable, okay. But CH3 and C2H5 different groups are there, then it is not superimposable. If it is same group CH3 CH3, then definitely it is superimposable. You can say that. If it containing a chiral carbon atom, then it gives non-superimposable mirror images. Therefore, the compound is said to be an optically active compound. Optically active compound. Is it clear? Yes. So if one more point I am going to represent here, that is racemic mixture, racemization, resolution, retention, inversion. Some terms we can represent here. Some terms. Okay. So racemic mixture, racemization. What is meant by the term racemic mixture, racemization, resolution, inversion, retention? And what is the product in SN1 and SN2? Already we have mentioned that in SN2 case, the geometry will be inverted, whereas in case of SN1, the geometry will be retention. But there is in some of the reaction, there is a possibility of both. For a same reaction, the geometry may be inverted or it may be retention. So means it gives 50% of both the compound. In that case, the compound is said to be optically inactive. So regarding that concept, we'll continue in the next class. Okay, thank you.